Good morning, everyone. Today we have great honor to have Dr. Susumu Saito to give the talk on real-time ionospheric monitoring using a dense GNSS receiver network. And Dr. Susumu Saito is a principal researcher at Electronic Navigation Research Institute, National Institute of Maritime, Port and Aviation Technology in Japan. His current research topics include ionospheric effects on GNSS, development of GNSS ground-based augmentation system suitable for the low latitude region, and ionosphere and space weather sciences using radio and optical techniques. He received his bachelor, master, and doctor degrees in ionospheric physics from Nagoya University in Japan. And I believe today's talk will be very interesting because in Japan, we know the network, in GNSS networks, we have so many data to support the ionospheric study. So welcome, Dr. Saito. So I think we could start the lecture. The floor is yours.
Thank you very much for your introduction. It is my great honor to have this chance to present my current research on the real-time monitoring of the ionosphere. So let me start my presentation. So the title is as introduced. It is on the real-time ionospheric monitoring by using a dense GNSS receiver network. So this is basically the as you know, the TEC and related work. But the key point is the real time. So this is the outline. I will start from some basic introduction on the GNSS measurement. And my real-time ionosphere monitoring includes two kinds of parameters or techniques. One is for the ionospheric disturbance monitoring. So it's a perturbation component, which is suitable for the transient events like TIDs or even sporadic layers. Another one is the ionospheric 3D tomography. It's a reconstruction of the 3D ionospheric density profile, and it is I found it very useful not only for scientific studies but also for the some radio application. So let's start. We have a number of very different various techniques to observe the ionosphere. For example, we have ionosphere, very classic one, incoherent scatter radar, very powerful to observe the ionospheric density profile. And these days we have we can even use the synthetic aperture radar measurement to derive the ionosphere. And what I'm going to focus on today is the measurement by GNSS network. We can derive what we call total electron content, and its temperature variation gives us very useful information. So let's go to the basics of the ionospheric measurement by GNSS. As you know, most of you know, the GNSS or Global Navigation Satellite System is a kind of radio navigation system, and position, timing, and timing are estimated by measuring distance between the receiver and the satellite. And there are a number of constellations. The GPS from the United States, GLONASS from Russia, Galileo from Europe, Beidou from China, and also Japan operates the QZSS. And the GNSS measurements include a number of various errors. For example, clock offset, ionospheric delay, tropospheric delay, and multiplex or thermal noise, etc. But this also means that the GNSS measurements include the information of the ionosphere. And we utilize the property of the ionospheric delay, which is proportional to the 1 over square of the frequency. So we can derive we can actually estimate the total electron content or the total number of electrons between the satellite and receiver by using the GNSS measurement. It's now with two or more frequencies. Yeah, this is so the TEC along the satellite receiver path or slant TEC is estimated by using the linear combination of measurement called or phase measurement of the two frequencies. But we know that there are biases between interfrequency bias, which comes from which arises, which is due to the different hardware delay in the satellite as well as in the receiver. So we need to estimate this bias. And another thing we need to consider is the code measurement. The upper one is it's free from the initial phase ambiguity, but very noisy. So often we use both, and because carrier measurements are very accurate. So we level the carrier TC to code TC to have better, less noisy the TC. But we still have the interfrequency bias, so we need to estimate the interfrequency bias of the satellite and receiver. But we use okay, so the interfrequency bias, it is most of it is constant, or it changes very in long time constant. So we can assume that these are constant, and by combining many measurements by many satellites and receivers, we can estimate these biases by using the least square method. So by estimating the yeah. So these biases after applying these bias correction, we can have the absolute TC. And then we can convert the slant TC back to vertical equivalent TC. Without bias estimation, the conversion from slant to vertical becomes very erroneous. Okay. And actually using the use of the dense ionospheric component derived from dense GNSS network has been done for actually a long time. This is the result from the paper published in 1998. They used the dense GNSS network over Japan and showed that if the medium scale, this is medium scale traveling ionospheric disturbances or MSTID, can be very clearly visual. And my work was to make it into real-time analysis, so that we can see the ionospheric disturbance over very quickly, and can be applied to various radio applications. And in Japan, we have a dense GNSS network called GeoNet, or which is the Japanese continuously operating reference station network, and it's maintained by the Geospatial Authority of Japan. And it now consists of about 1,300 stations all over Japan, as plotted on the left-hand side. Actually, if we plot, even without the coastline, we can easily identify the shape of the Japanese island. And now the GeoNet tracks GPS, GLONASS, Galileo, and QGSS. Unfortunately, Beidou is not yet, the Beidou data are not yet provided. I think that it will be available in the near future. And my institute, Electronic Navigation Research Institute, collects actually receives real-time data from the 200 selected GeoNet stations, which is shown on the right-hand side. Actually, our institute, my institute, is not only for the not particularly for the ionospheric study, but more and more on the application side, especially for the air navigation, aircraft navigation using GNSS. So we have a lot of GNSS-related studies and experiments. So that's the reason why we receive the real-time data from the 200 GeoNet stations. So we use some limited data from GeoNet, but in real time. Okay, so by using these the measurements from GeoNet in real time, we observe the ionospheric disturbance in real time. So first parameter is the perturbation component of TC, or we call DTEC. It is kind of a detrended TC with a certain time constant. The advantage of this technique is that this is the perturbation component. So the interfrequency bias is is eliminated by taking perturbation. So it is actually easy. The analysis is rather easier and suitable for real-time analysis. What we do for the real-time is that we fit the previous fit the TC in the previous time period. In this in my standard analysis, the time interval is 60 minutes or 1 hour. So we fit to the TC in the previous 1 hour by using a polynomial function and subtract the fitted one to derive the variation component. So this one, the difference between the observed and predicted or fitted TC at time t is considered as perturbation in the ionospheric delay or delta TC. Then, for example, on the right-hand side, if we have this quite TC variation looks quite smooth, but if we take the same technique as shown left-hand side, we see this kind of periodic variation of amplitude of about plus minus 1 degree. So actually, this is quite useful. And another one is another parameter which is suitable for either shorter time scale variation as the ROTI or rate of TC index. And it is basically the standard deviation of the time derivative of TC in a certain time period. Typically, the 5-minute interval is used. Okay, so the DTEC and the ROTI complement each other because the delta TC is more suitable for rather longer time constant, and ROTI is suitable for short time scale transient events. Okay, so this is the real-time data analysis system for our in our institute. We have many GeoNet stations, and raw data at one hertz sampling comes to a GeoNet server. So the left-hand side is on the GeoNet side. And every receive raw data, one hertz real time to our data server. The analysis is taken every 5 minutes, and perturbation TC map is published on the web server every 5 minutes. And currently, the processing time is about 2 minutes to process whole the 200 GeoNet station data and publish on the website. This is an example of our observation of Loti and delta TC during the famous event the Tonga eruption on 15th January 2022. The top row shows the Loti associated with during the, let's say, in the period following the Tonga eruption. Now we can clearly see the enhanced Loti region in a few localized locations over Japan. The bottom row shows the delta TC component, and okay, and we can create we can find two different wavefronts of the TIDs following the Tonga eruption. And the first one was actually considered to be the disturbances mapped from the southern hemisphere along the magnetic field line. And second one is considered to be the atmospheric wave propagating over Japan. What is important is that these analyses were conducted in real time, and we could see these perturbations almost in real time, just a few minutes here. This system allows me to analyze the effect of the Tonga eruption just soon after the event occurred. And actually we also, okay, I will introduce the absolute TC real-time measurement later, but we also have the absolute TC measurement, and very interestingly, we could see the correspondence between the Loti enhanced region, so with the small scale irregularity region, and TC enhanced region. And these correspondences were also seen in almost real time. And another application was for the sounding rocket measurement of the ionosphere. In August of last year, a sounding rocket was launched into the ionosphere to study the physics related to the MSTID. And because we need to know if the MSTID event is occurring or not, just before we decide to launch a rocket. This real-time monitoring system was used to decide if the rocket should be launched or not. Of course, in post-processing, we are actually analyzing we are comparing the TC data with the sounding rocket measurement data. The Loti is also can also be used to detect sporadic E-layer. These two figures compare the Loti map mapped at the different ionospheric heights. And you can see that if we map the LOTI values at 100 kilometer altitude or E region altitude, we see the clear structure as indicated by white over. But if we map on the at the 350 kilometer or F region height, the structure was not seen, but the LOTI values, LOTI enhanced regions are scattered. So it strongly suggests that the disturbance or irregularity causing the LOTI enhancement is around the 100 kilometers. And actually, when just below this LOTI enhanced region, we have Kokubunji ionophone station operated by National Institute of Information and Communication Technology, Japan. And we see that we had a very good correspondence between the LOTI enhancement and sporadic occurrence. Furthermore, this is a time series of ions from the measurement and LOTI over the ions from the station. They have a very clear correspondence. So the structure seen in the LOTI map is considered to indicate the structure of the sporadic relay. Actually sporadic E is important on the radio propagation. As we are studying, my institute is studying on the air navigation system. We are interested in the anomalous propagation, the interference effects due to the anomalous propagation by sporadic E layer. And we can also use we are collaborating with my colleagues of University of Electrocommunication to monitor the anomalous propagation from aeronautical radio stations in East Asia region. And we combine those measurements and the LOTI measurements to detect the sporadic E propagation in almost real time. So now these LOTI and detect maps are available in real time at this website. The updated every 5 minutes, 2 minutes latency, and also on the website we can only see the plots, but delta TC values and the LOTI values are available upon request. Just contact me. Currently we use GPS only, but the use of multi-constellation included in GeoNet data is under test and will be available very soon. And we use this real-time service for the situation awareness for ionospheric disturbance for the the radio application, and also for the scientific purposes, especially for the ionospheric, the disturbance dynamics. Okay. Yeah, we actually have already operated this system since, let's see, 2014. So we already have almost one solar cycle data. And we will continue the real-time observation continue. The next topic is the ionospheric 3D tomography. And again, this is also for the in real time. The GNSS tomography is a technique to reconstruct the three-dimensional ionospheric density profile from many observations of the total electron content. The key point is to have TEC along different line of sight between the satellites and receivers. From the TEC measurement, TEC is an integrated value, and we reconstruct or we solve an inversion problem to reconstruct the three-dimensional electron density distribution. And usually it is an ill-posed inversion problem and not easy. It's not straightforward to solve the inversion problem for the tomography. This is a basic equation. So TC measurement related to the electron density by a geometry matrix. So basically, the problem is to solve this one for electron density vector. But as I mentioned, it is not easy. The information is limited. So we need some tricks or to have better solution. So we defined a cost function to be minimized, and we introduced two terms. First one is the least square term with actual boundary condition. We fix the electron density at the top and bottom, and second term is the what we call constraining term, or which defines how smooth the ionospheric density distributions are. And this weight function W consists of a parameter which defines how the adjacent electron densities are similar. And the minimization of this cost function can be solved analytically, and we have this equation. But this is again not easy because it requires a huge matrix inversion. Nevertheless, we succeeded in making it into real-time, a near real-time operation. This is the center part is the tomography conversion inversion volume. The smallest, the finest resolution in latitude and longitude is 1 degree, and the height resolution is 20 kilometer in main part of the ionosphere. Now we operate this system to produce the ionosphere, the 3D density profile every 15 minutes with about 6 minutes latency. But now it's updated to be 3 minutes latency. It was basically by the update of the hardware, and we validated with the results of the tomography by using the incoherent scatter measurement by the MU radar operated by Kyoto University, Japan. And a top panel shows the comparison of the ionosphere peak density, which shows the very good agreement. And the bottom panel shows the peak height, and we see that when the ionosphere peak height is higher than a certain level, they reproduce. Tomography can reproduce the peak height quite well. But when the peak height goes down, the peak height, well, the tomography couldn't follow the peak height. So we made an improvement, which is published published by Sesanga et al. In GPS Solution 2019. And it is basically an assimilation or adding more information on the ionosphere peak density and height by using the ionosonde measurement. So, and also another point is to estimate the electron density as a positive definition. Okay, maybe we can keep this. But basically, it is an assimilative process. So first, we estimate the original tomography and modify the results of the original tomography by introducing the ionosonde measurement. Then we got a better result for the ionosphere peak height. The left column shows the original result of original tomography, and the right column shows the MU radar incoherent scatter measurement result. And the medium and the middle column shows the modified tomography. And we see that the ionosphere peak height was reduced from the original tomography and closer to the incoherent scatter measurement result. So this is the block diagram for the real-time 3D tomography. We get the GeoNet data from 200 stations in real time, and we every 1 hour we estimate the satellite and receiver interfrequency bias. And the every 15 minutes, we derive TC and apply the interfrequency bias remover. And we get the absolute TC. And then we apply 3D tomography, and we also receive from the ionosphere the data from NICT also in real time. So we use actually auto-scaled the ions on the parameter. And finally, we get the electron density profile. Okay, and this is, I've introduced some ionospheric disturbance reconstruction. As this is the same event I introduced previously. It was on the 15th January 2022, following the Tonga eruption. And the right-hand side is the absolute TC. We see two regions with the TC enhancement. And we can click OK. So the left-hand side is the cross-section of the ionospheric density profile along these two longitudes, 127 degrees east and 135 degrees east. And we see that these the peak of the ion peak density was found between 300 and 400 kilometers. And if we compare, or if we take the difference from the one day before, we see that if the density at 300, 400 kilometers increased, and the density below 300 kilometers was decreased. Yeah, this means that in this ionospheric density enhanced region, the ionosphere was elevated as compared with the previous day. Now, this is a longitudinal cut, and we can also see the westward the structure was inclined from the southeast to northeast, and again the region of the electron density enhancement was associated with the elevated ionosphere. Okay, maybe. And by using this information, we could infer the ionospheric, the physics or mechanism to result to cause this kind of phenomenon. Maybe we can skip this. The key point is that this kind of ionospheric density profile and variation from the previous day are available in near real time. Now there's just 3 minutes delay. And the real-time 3D tomography service is available on this website, and you can choose any time instant and you can choose different uh, uh, sorting method. And this ionospheric density values are also available upon request. The this the also because my institute is more on the radio application, we try to apply this 3D tomography for GNSS. For example, by using the three-dimensional three-dimensional ionospheric density profile, we can estimate the ionospheric delay for arbitrary satellite and at the arbitrary location in Japan. And we tried to apply the ionospheric delay correction for single frequency user by using 3D tomography. And we found that the the you know, the position error was very much improved, and also the scattering or noise of the measurement was less than the dual frequency measurement. So this is one of the potential application of the 3D tomography for GNSS application. Also, we collaborate with National Institute of Information Communication Technology to predict the HF radio propagation in real time. In this real time HF radio propagation prediction, our tomography results are used for the regional propagation prediction. So the real-time 3D tomography is not only useful for scientific purposes, but also for the radio application. Yeah. Okay, this is the summary of my talk. We realized real-time ionospheric monitoring, and it is actually very useful, both for scientific and engineer application. And we provide two types of real-time data services, two-dimensional TC variation, and a 3D ionospheric density profile by tomography. So, yeah, I'm very happy to contribute or to share our data, and I hope you could visit our website and try our results, and hope to have more feedbacks. Thank you very much for your attention.
Thank you, Dr. Saito. It's really very detailed presentation showing the 2D and the 3D atmospheric products. Very fruitful research results. I'm very happy to see the series of work, and especially for the application. In the application, the products are available, from the website and very useful to society. This is quite good translation to the users. Any question from the audience? Yeah, if you have any question, you can also write down from the chat.
Yeah, I see one question in chat box.
It's oh yeah,
from India. Yeah.
yeah.
So my query is whether there is any classification scheme of LOTI to detect the severity of the irregularities.
Mm.
And it's
Mm.
the same LOTI magnitude classification. Yeah, I think it's a good question.
Yes.
Yeah, and it depends. Actually, the severity depends on the region, especially magnetic latitude. If we go
Mm.
down uh, to low latitude, the LOTI can be quite high
Mm.
due to the plasma bubble related irregularities. But if we go higher and higher latitude, LOTI uh, tend to be lower. So I think, yeah, I don't think that there is a common, well-defined classification scheme. But yeah, we need to check. Yeah, if we look at the data, then we can have some insight. For example, over Japan, which is lower mid latitude, uh, yeah, for ROTI plus minus zero point 0.5 TEQ per minute. It's my rough criteria to find the strong uh, disturbance.
Yes, I agree with you. Yeah, maybe we could define a regional scale, for to classify the different uh
Yeah, yeah,
levels of yeah. Mm.
yeah. I think so. It is useful to have a common
Mm.
criteria. Yeah.
Mm. Mm. Indeed, very good question. Um, any question? Any other questions? Yeah, I have two questions. Firstly, I no, the first maybe not our question. I like the idea, about roti. You provide uh the roti maps at different layers, like 100 kilometers and then 350 kilometer. I like this idea. Indeed, the roti map is 2D, right? We could not know the real height, the location where the irregularity occurs, And about the tomography, could you go back to the strategy? You introduced the understand data and the IR model. That
Okay.
one. That's just like yes. Uh, I understand the to solve this yield post immersion problem, we need to add a constraint, and I like the idea of this. I introducing ionosound data because this is from measurement. We trust that, but I have a question: why you introduce IR model? This monthly average values, should we trust that?
Now, this IRI is just to get to have FOE value.
Okay, but
And this
mm,
is okay. Yeah, I need
mm,
to describe the equation to estimate the HMF2 from ions on the value.
uh,
Actually there is an equation to estimate the HMF2 or true the height, F2 peak height. And
uh-huh,
in daytime, we need to correct the retardation or propagation delay in the E region.
uh, uh, oh, I see. Um,
From the real-time auto-scaling ionospheric, it is not easy to get FOE. But the E region peak density is rather well obtained by the model. So IRI is just used to obtain the E region density to correct the to get better HMF2 estimation.
Yeah. Regarding the positioning validation, you test without the single frequency positioning result without the ionospheric correction and tomography correction and the dual frequency. Yeah, that's one. Okay.
So basically, if we don't apply ionospheric correction, actually the ionospheric delay appears as a vertical, more in the vertical position error, and usually it comes into it introduces the positive error. That means the position is estimated higher. Yeah, it's a bit opposite to the intuition, because the ionosphere delays the propagation, but after estimation, the position error, vertical position error appears in positive. And this is mainly due to the ionosphere. And you can see if we use dual frequency measurement, then we can remove the vertical position error due to the ionosphere. But by combining two frequencies, we know that the error was random error is enhanced by factor 2.6. Yeah, it is due to the combination of two frequencies. So that means we introduce
the noisier.
We add the noise, and also to eliminate the ionospheric delay, it further introduces the amplification factor and finally we get 2.6. So that's the reason why the scattering is higher for the dual frequency correction. But using single frequency, we have a smaller noise, but better ionospheric correction by tomography.
I think we have more questions from the chat.
Yeah, what is the confidence level of the hydroid of the CD? Yeah, is this height structure due to uneven distribution of the? I don't know. I think yeah, the uneven distribution. If he mentioned about this one, the discrepancy of the peak height, it is due to the kind of the constraint term introduced here. So the ionosphere can't be estimated so lower. That's the reason why we introduced the ions on the assimilation to further further change or the or modify the tomography results to be closer to the observation. And the next one, with regard to the massively increased emission, civilian or government, or were you observing any lingering effect disturbance to the ionosphere? So how quickly did the layers in the atmosphere come return to origin? Yeah, that's it's a difficult question. I think the the numerical modeling of the ionosphere and thermosphere may answer this question rather better. Oh, but, for the yeah, as long as in general we know that the geomagnetic storm continues for a few days. And ionosphere also responds to the magnetic storm, geomagnetic storm. And the ionospheric density variation continues, I think 2 or 3 days following, at least 1 or 2 days following the geomagnetic disturbance. But to better understand I think better to refer to the modeling data. Okay, I think this was already answered. Are you using any low-cost GNSS receiver to reach such huge number or in geodetic graders? Yeah, this is a very good question, and we are actually evaluating the low-cost GNSS receiver, and yes, actually the low-cost GNSS receiver, such as u-blox F9 or u-blox receiver with dual or triple frequency capability performs quite well. We can estimate. We can use those
non-geodetic receiver.
Non-geodetic receiver, but the issue is the antenna.
I see.
Yeah, we actually we need a good antenna to have better multipath rejection and phase variability between the different frequencies. So the antenna is now an issue. A good antenna is very expensive.
Okay. I have another question. You mentioned that you will provide multi-constellation route maps in the near future, right?
Yes.
What benefit do you think we can get from the multi-constellation for route map? The more IPP points or any other advantage? Yeah.
Basically more IPP.
Yes. Okay, but
so wider coverage. Yes. If we plot the IPP, they are not so dense with a single constellation. And also the satellite orbit, especially by using GPS, the satellite positions are repeated almost every day, just for minutes shift. So we often have let's say, the region without GPS observation, and it's repeated for some days. It's
Uh-huh.
actually yeah. Sometimes it is a region where we want to see the disturbance,
Uh-huh.
but adding more constellation, we have wider coverage.
Uh-huh. I'm curious. Sorry, yeah, I take the advantage of being the host. Sorry for that. I am curious about, yeah, I see very excellent work you or and your team have done during so many years. I wonder how many people are there in this team? How many people working on so the tomography, this product
Okay.
application? Yeah.
For tomography, the I'm actually responsible for the real time part,
Mm-hmm.
and we have uh, the one student working on the improvement
Uh-huh.
from a university, and his
Mm-hmm.
supervisor. And
Mm-hmm.
also this guy, uh, uh,
Mm-hmm. Yeah.
the Sanga, Nicolas Sanga, unfortunately he's now outside Japan. So for tomography,
Uh,
or maybe yeah, uh, basically three, including myself, is working on it.
mm,
And for the Loti and Delta TC map, yeah, it's mainly uh, it's almost done by myself only.
okay.
But we have a few colleagues in university, for
Mm-hmm.
example, doing this kind of anomalous radio propagation
Mm-hmm.
measurement. So we are collaborating with uh, some universities outside my group.
Okay, I understand. We have also one other question from the chat. By Han Tingwei from CAS in China. Yeah, I think it's also a good question.
Yeah,
Can we
good
use?
question. Yes.
Yeah, yeah, yeah.
Radio are also radio occultation PC. Yeah, actually, we also considered about it, but it's not
Mm-hmm.
easy because
Mm-hmm.
it has very long propagation path along the in horizontal. So it goes
Mm-hmm.
through the outside the tomography inversion volume. So
Mm-hmm.
uh, we think that it's better to use the 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 density profile
Mm-hmm.
uh, derived from the radio occultation. It's rather easy to incorporate into the uh, so not the TC but the uh, inversion.
Immersion. Uh-huh.
After inversion, the density profile can be incorporated into the tomography, like ions on the day.
Mm-hmm. Especially for real-time application, I don't know if the radio occultation data is available in real time. Some yes, right?
Yeah,
But do you think the POD data would be helpful for tomography? The
the
LEO, a POD,
Leo.
from Leo, yeah.
Yeah, yeah, I think so. If the uh, only even for the offline, uh, the I think real data could also be because there are so many measurements, so many satellites, so we can. Yeah, I think so.
Okay. Okay, the last question. Sorry, because we have limited time. The last question from Slamet about the resolution of the tomography.
I have the resolution to see the quality of every error or degree of view at the resolution matrix or resolution map to check the result.
I don't quite understand this question. The resolution, what's resolution matrix?
Yeah, the quality of every. Yeah, that's. Do you add the resolution matrix or resolution map to check? Yeah, actually, we could check our results only at the location. Okay, the number of yes, yeah, yeah, yeah.
I understand.
Actually, yes, we have yes. Internally, we have the number of paths in
each voxel.
in each voxel. Yes.
Yeah.
I need to check it how it was used, but yes, we have those values. We use those values internally. Yes.
Okay, we ran out of the time a lot.
Yeah, thank you.
But I really enjoyed the talk, given by you today. So thank you so much, and thank all the audience for the participation. So yeah, that's all we can post today's lecture.
Yeah, thank you very much.
Thank you. Thank all of you.
I enjoyed the discussion quite much. Thank you very much for your invitation. I'm very happy to have this lecture. Thank you very much.
Thank you. Have a nice day.